Hello community, so great that you are back. Yes, today we're gonna have a look. You are building your multi-agent AI system now, and you have an agent A, it's beautiful. You have an agent to agent protocol, you have other agents. Those agents have an MCP protocol. You can connect to all the different tools, you have all the external data coming in. But it's not really working because there is a bottleneck in your system. So let's talk about it, how you can optimize your AI. And you know what we're going to talk about? We're going to talk about the world model, because it turns out some of our LLMs in our agents, they do have a world model and some don't. And some do have a real powerful world model and some are rather limited given their specific parameter and their learning. So what to watch out for? Let's start here. So a world model, of course, a world model. Everybody knows what a world model is, no? But we need to have a deep dive into the context here within our artificial intelligence configuration. So let's start. Maybe we should give a meaning to it. And here it's a very simple one. In AI and robotics, a world model is more or less an agent's internal representation of how the world works. So this may include now a partial knowledge of physics, how objects interact, what is gravity, what are here object properties, what are these things, no? What are they made of? What are their expected behavior if we think AI predictive behavior? What are their spatial relationship? Where things are relative to each other? What are then their causal relationship? If I do X, then Y will likely happen. What is specific domain knowledge that I have to integrate? This means knowledge about specific areas, topics, and really important in multi-AI agent system, the agent intention, the behaviors. How other agent might act in my environment. And this can be other AI system, people, animals. What is the expected behavior of objects? This is what we say, this is a world model. But this is not precise enough, no? Because think about it, in essence, a world model in an LLM, in an agent, at the core of an agent, is a complex web of statistical relationship and patterns this system has learned from text. And let's start with an LLM before we move on to vision language models. And learn from text, which allows it to simulate an understanding. It simulates an understanding of all the concept, of all the entities, and what we human would call a common sense. But all of this only described in that text, in the pre-training dataset. And for the first step, we limit ourselves to a large language model, and therefore we only have text, semantics, linguistics. Now, this is something I told you, this is a world model, but this is just my human representation to communicate to other humans. But this is not a world model, because this has a visual interpretation where I want to show you, hey, some world models have huge holes of knowledge, where there's no pattern connecting topics or relations or domains. Maybe this is here the complete financial domain that is excluded here from the learning hyperface of this particular LLM. Or maybe here we're missing out, I don't know, on physics or mathematics or causal reasoning. Maybe this blue here is just beautiful code experience, but we are missing out on 3 other subtopics. So this learning hyperplane, or if you want this world model visualization, I've chosen for the particular reason that you see this is not a continuous coherent hyperplane in a multidimensional space. It has holes, it has disconnected areas, and it has a different structure in these multiple dimensional spaces. It can be a simple or complex one. So it is not easy what is a world model. Let me give you this. You say, hey, that's simply a map of the Earth, yeah? What? The textual description, and we are here in a world model in text. We are here in statistical relationship, in patterns. So the simplest model might take, what I see is vast blue expanses dotted with varied land masses. So you see, the textual context, the linguistic difficulty, a simple LLM might associate with this particular image, if it's a vision language model, is different to the next one, where we already start to give names, no? Interconnected blue oceans, the Pacific, the Atlantic, the Indian, the Arctic, and the Southern Ocean, covering most of the surface, punctuated by distinct continents. If you want, here learns here the name of the oceans first before it learns here the name of the continents. World models are really specific to LLMs. So an LLM world model is an implicit, internal, learned understanding of the relationship concepts, entities, and common sense knowledge embedded within that particular training data the LLM was trained on. And now comes the beauty. This is an emergent property that arises from the model's training objective. Predict the next word or the next token or the next sequence of token in a sequence, in a linguistic sequence. And to do this well across trillions of worlds, within our neural network, the model must now learn underlying patterns and maybe underlying symmetries. Vector spaces we build close by semantic meaning patterns about how things relate in the real world, and now we have to break it down into a two-dimensional text hyperplane. So we lose a lot of the complexity of understanding what is a world, and therefore we call it a world model. So which LLM has now the best world model? Does every LLM has a world model? How are world models different? Well, here I show you 3 of my world models. And of course, you always have agent-to-agent communication protocols, and you have always here the, if you want, agent MCP model context protocol to the tools. Great. But just that, coming back to the question at the beginning of this video, what if I connect multiple agents? Is the complexity or the world model, 1, 2, 3, of those LLMs important for the complete multi-agent system? Is it that the weakest world model in an LLM is the weakest chain link, if you want, in a huge multi-agent chain? Does this determine the complete performance of the system? And if so, how and when? And what about we have an MCP to specific tools here, or we have it here an MCP connection from this very simple world model? What are the differences in the performance that we can expect? And does it make sense that you pay for an LLM, really expensive, and then you connect it here for model context protocol data extraction from tools with those agents, what you should be aware of? So let's start. And yes, we have a brand new study, and this is here from Google DeepMind. And here to answer the first question, does every LLM have here a world model? And the answer is, well, it depends. And luckily, here you see the first 3 pages of an 11-page mathematical proof that given particular boundary conditions and particular error fluctuations and particular start conditions, yeah, a complex LLM can have a world model. And I would say, this is exactly what I was looking for. Well, of course. So let's have a look at this in my last video. And my last video I published only to be able now to tell you, hey, look, what we achieved in the last video here was the following. The LLM generated something out for us, no? And it generated here, for the cases of an orbital data center, different components. Solar energy collection system, battery energy storage unit, thermal loop, phase-changing thermal reservoir, and so on. So what it did, it created here a causal chain in its own temporal logic of how it imagines the world. So if you want our O3 model from OpenAI, when I had this cascading complexity, it created world models. And I tasked now the system to create for each and every level a different world model. Where a simple world model, then we add complexity, and the complete causal interrelation of our world models went up and up and up. So our world models became more and more complex. And I told you, if you make this an auto-run, you see exactly when O3 is not able anymore to hold this complexity into its own system. And yeah, I have here a particular prompt where I see exactly when O3 tells me, hey, sorry, I give up. This is too much. I can't solve this anymore. The complexity I created is now so high that I cannot build a world model anymore. I terminate now as an AI. This is exactly the breaking point I'm examining now if I test LLMs. So the world model is something absolutely fascinating because it gives us here, if you want, a higher simplified representation of what an AI, let's say here our O3, is capable of. With a more complex world model, we can bring the LLM to its absolute limit. And this is what I'm interested in. And you might say, but wait, how does the LLM or the general agent here, in our case, understand here the causal behavior of those elements? Because those elements is what it learned from its pre-training data. And yes, there's a solar energy collection system. And yes, there's a battery energy storage unit. But hey, what if I bring this to the low Earth orbit? I have complete different pressure, complete different temperatures. If I have here eclipse, non-eclipse situation, it will have much more stress factors. What about vibration here in the systems? No? How will this now behave differently if I build a different world model? Welcome! Because this is exactly what Google DeepMind examined. And Google DeepMind started here with June 2nd, 2025 publication on general agent need world models to function, and they were the first providing a new algorithm for eliciting world models from agents. This is especially interesting for agents we have no access to, non-open source proprietary like O3 by OpenAI. And they tell us here any agent capable of generalizing here at least the multi-step goal-directed tasks must have learned somehow a predictive model of its environment. And now this is important. And it's not just a model, it's not a passive, it is a predictive model. So we can have a look into the future, so we can apply an autoregressive model, and it is a prediction about the environment. So the AI does not only reflect on its own action on all possibilities, but it also understands that the environment can have a dynamic evolutionary scenario. And it is now the task to predict this model. So if you ask me, how does the LLM understand this? You ask more than just, hey, how does it know that there's a solar energy collection system or a battery energy storage here in the orbital data center? You ask, how is this interconnected on a real physical level? Now, talking about a real physical level, 2 days ago, we have here a new publication by MIT, UC Berkeley, Caltech, UCLA, and they talk about exactly this. Principle-based physics, reasoning benchmark for LLMs. And in this study, they have some beautiful insight, and they say current LLMs often fail, and I will show you 7 LLMs in detail, to emulate here the concise, principle-based reasoning characteristic of human experts, instead generating lengthy and opaque solutions. That might be absolutely incorrect. So if you thought that an LLM today, here in June 2025, is really able to describe here an external environment to itself, I have to tell you, well, we have still to deal with some challenges. Let's have a look. Their studies show, and please have a look, it's a beautiful study, it reveals here a consistent failure to align with expert-like reasoning paths. Now, there is something special to this study, and if you read it, you understand immediately it is not just about physics and theoretical physics or theoretical chemistry, about the reasoning process. But they focus here on a very specific subset of an intelligent subset they call a principle-based physics reasoning. And they develop a data set and whatever, but they design these particular problems to be solved easily. I mean, easily now, if you're a theoretical physicist or have a PhD in mathematics, using physics principle reasoning. So more or less, you have 2 options how to solve this. No? You can go to a computer and you have your numerical simulation programs for high energy particle collisions or whatever, or you just can use your brain, your understanding of the physical law of the Feynman diagrams, and you say, hey, wait a minute, here I know that there is an inherent symmetry to the system, and whenever I have a symmetry, I have, if you want, some other mathematical elements in the theory. Yeah? And you know exactly what I mean if you are a theoretical physicist. So let's have a look at this. How they built this. There, you see, half up is just about the symmetry, the internal symmetry of theoretical physics. And you know exactly what I mean, Gauge, and so on. And then we have dimensional analysis. You can solve so many problems just by looking here at the dimensions. Unitary transformation. You have some symmetry here on a molecular level or an atomic level. You can look at the topology. You can have even simple equation of motion. And you remember we did a deduction just from some principles, first order principles. So I just give you the result. So here you have the accuracy of LLMs given here 3 different degrees of difficulty. We do apply a zero-shot test. This means no further information. We just say, hey, this is the problem. Give us your solution. Difficulty, you have color-encoded E for easy, medium in orange, and difficult here. You see green. Interestingly, they have now Gemini 2.5 Pro, and you see this is here the best of their models. Then, so Google, then they go with OpenAI 04 Mini High. Then they go here with Claude 3.7 Thinking, the max thinking model here from Anthropic. And with the, unfortunately, with the old R1 DeepSeek that is almost half a year old. And then they go with here the Claude 3.7 non-thinking, the GPT 4.1, and the version 3 of DeepSeek. And you see there's quite a difference, no? And you remember here in the video that I showed you the crazy LLM test and we looked at the ARC AGI leaderboard. And I told you, look, there are 2 very close by performance data. We have here Claude 3.7 with 16K thinking. And we had the ARC AGI 1 score of 28%. And this was even better than the ARC AGI 1 score of Opus 4 and thinking of 1K. That's even less expensive. So this was quite an intelligent choice here, I think, by the authors. And also you see, even in this ARC AGI 1, that the old DeepSeek R1 was not as performant as here the Claude 3.7 thinking 16K. So this is absolutely here what I would expect looking at the other benchmark. This sounds good. Yeah, you could have maybe have the 03 model, but 04 Mini High is absolutely a beautiful contender from OpenAI. And the Claude 3.7 here, the maximum thinking model, is a good choice. Yeah, the other GPT and whatever. So you see, this is, I would say at first glance, I would say, yes, I understand this. This is also what I found also in the literature here from other performance benchmark tests. And other authors tell us, hey, we introduce now a PhySense, a new novel, human-curated. Imagine in June 2025, somebody is really creating something by human. Wow, it's amazing. No synthetic data set created here on principle-based physics reasoning benchmark on evaluation scientific problem solving. And they have here 380 carefully designed problems from all different ways: symmetry, reasoning, dimensional analysis, renormalization, group analysis, topology, and quantum dynamics. Plus, they have 3 prompt strategies, like I showed you the zero shot. Then you give it a hint. You say, hey, you know, there might be, look at this parameter, because if you... and no computation. And no computation will become important. And I want to give you a feeling for this problem. So here, the simplest problem you have here, you have a uniformly charged plane in space. The plane is a square. The 4 corners are x, y, z. And which of the following locations in space have the x direction electric field strength equal to the y direction electric field strength in both sign and magnitude? Now, if you know theoretical physics, you say, hey, that's an easy thing, because you know that this electric field has an internal symmetry, no? Especially if your plane is a square and everything is so easy to solve. But you know, yeah, look at the answer from Gemini 2.5 Pro with zero shot. So you give no information at all. You just say, this is the problem, solve it. You don't have in-context learning, nothing at all. And Gemini 2.5 Pro will start electric field component in a uniform chain square plane, but the coordinates are given here by this integration, and then we just calculate this and looking for the points, and yeah, but yes, and it gives you an answer, A and B. Now you know this is the wrong answer, but you see, it is not seeing the inherent symmetry of principle-based theoretical physics questions. It is trying to calculate this, and it fails because it's a vision language or a large language model. If you ask a human, the human would tell you here it is the answer A, E, I, J, N, R, and V, and whatever, you know, simply a symmetry-based answer. And now the authors here, MIT, Berkeley, Caltech, UCLA, say, hey, overall, especially now the non-reasoning model, so the non-thinking models where you know that this is an active thinking model, they even demonstrate a more shallow understanding of physical principles. And often, if they apply them inconsistently, showing here a tendency to latch onto terminology without a true comprehension. So this is, if you are into this particular domain knowledge, maybe not the best way is to go with non-reasoning models. Another example. Let's have here an example on quantum dynamics, a very easy one. You have here a quantum spin chain prepared here on the Hamiltonian that is given. You have a time evolution, which is the following elements here is true in the final state. And if you look at this, you immediately, as a human, you see the symmetry. No? You have multiple symmetry layers. But if you now look at an AI might not have this insight. And here we come now to the non-computation prompting. And the authors tell us, hey, we observed that in some LLMs, particularly the reasoning models or the strong reasoning models, they may default to complex computational approaches, you know, MCP, A2A, whatever goes on. Yes, beautiful C++, obscuring here the application of fundamental principle and leading to overly convoluted solution. In this setting, models were explicitly instructed to avoid here the complex computation. Non-computing prompt were given, and instead focus here on a principle-based reasoning structure. You don't have to compute here the quantum spin, because you easily see from the text that there are inherent symmetries in the system. If the AI is able to find them and to notice them. And so this says this strategy aims to assess if the LLMs can prioritize simpler, principle-driven solution when they are not allowed to do numerical computation. And I want to just give you here all the beautiful different answers. Ne? So the O4 Mini High with a hint prompt where I tell them, hey, buddy, there were some symmetry in the system, so please activate your symmetry analysis. Comes back and gives you here this. Ne? And says here A and Z. And O4 Mini High with the non-compute prompt where you just say, hey, please do not try to compute anything. Just think logic about this from first principle. As then this explanation. And then we have GPT 4.1 with the hint prompt. Yeah. Oh, it's really beautiful. Yeah, what the AI tries to argue. And here you see a reflection looking at the reasoning process. If it is a real reflection of the reasoning process, just how strange the system understands physics, and maybe the AI system does not understand physics at all. Maybe it's just pinpointing some vector somewhere in the space and think that there might be a correlation because there was in the pre-training text a semantic correlation that is not at all a causal relation in the real world. So this is a beautiful test where you see now the internal reasoning process that just goes crazy, and maybe it finds one or maybe even two symmetries here, as you see, but it's missing out on the general structure and it's missing out on the general solution. So absolutely fascinating to see. But on the other hand, I have to tell you, if you would have told me 2 or 3 years ago, hey, imagine I would give this particular problem to an AI, do you think it would be able to solve it, I don't know, to 1/3 or half of the answers? I would have said never ever would an AI system be able to do this. No? Now we see that those models try. Sometimes they are lucky, sometimes they fail completely, but we are not there yet. And the authors tell us, hey, we focus here on the predictive world models, which can be used by agents to plan. And you know, the planning exercise by any agent is the most important step. Here's where you put in on the strategy, how you want to approach this, how you want to tackle this problem. And after the planning, definition of the world model used in reinforcement learning, and especially in reinforcement learning with all the methods I showed you in one of my last videos, this seems to be really the right way forward to understand here the interaction with the environment states. And for a model-based reinforcement learning agent, explicit world models are usually one-step predictors of the environment state, which in a Markov environment are sufficient to predict the evolution of the environment, the dynamic of the environment, under arbitrary policies. And this is here one of the parts that here the authors here from MIT, UCLA, and Berkeley, they really give us here. They say it's a proof. I would say it's a strong indicator that those models have to have an internal world model. And here, given the official wording, and the authors tell us our main result is a proof by reduction. We assume the agent is a bound goal condition agent. It has some lower bounded competency at goal-directed task of some finite depth n. And we prove that an approximation of the environment transition function, which is in the probabilistic view that we have on AI, nothing else than the internal world model of our AI, of our vision language model, of our large language model, of our agent, is determined by the agent policy alone with a bounded error. So this is now interesting, because the environment transition function, how the dynamic of the environment will develop step by step if we have a discrete environment developmental factor, this is our world model now. So absolutely fascinating that we are just at the basic levels at understanding here the reasoning and the decision making here of our AI system if they have to take into account an external environment. Now coming back now here to the examples you as my viewers had here with my last videos, you can ask, hey, what is the world model of a proprietary O3 model by OpenAI? Now, we don't know because we have no insight if you want. No, we're just given here if you want the result only. But you could now theoretically, probe, and let's say we have somewhere here the information that, I don't know, at a particular at a temperature, the system will switch. So what we can do, we can now manually probe here the complete temperature range and see when it happens. So let's say at 40 degrees, the O3 now tells me that it switched now to, let's say, auxiliary power. So I have now achieved, just by probing here the action, which is the policy, which is relevant and determines with an error bound the internal AI world model. I have now insight into the O3 world model. But of course, think about the complexity of the world subsection we even have to test here for an orbital data center. This would be an extreme expensive undertaking. But you see, now we understand, which is common sense, I think. If it just go through all the possible degrees of temperature, all the possible degrees what can happen, all the possible interaction patterns, all the possible catastrophic failure patterns, if you go through them step by step, you will see the reaction by the AI system, and therefore you are able to logically deduct the world model of O3. Also, it might take you quite some time. And at the end of the video, I'll always show you the official conclusion, the screenshot here of the authors. And they say, we have shown that any agent capable of generalizing to a sufficient wide range of simple goal-directed tasks must have learned an accurate model of its environment. Otherwise, it would not be able to predict it. So essentially, all the information required to accurately simulate the environment is contained in the agent policy. And this implies that learning a world model is not only beneficial, but necessary for general agents. So if this is true, and I'm not absolutely sure, between you and me that this is really a proof. I think this is a strong indicator. But okay, let's say this is it. This means if you have a very powerful, huge model, an LLM agent, then this agent, LLM, has internal found a representation of a world model. And this representation now kind of dictates here the probability distribution for particular action in particular states of the environment and of the AI system itself. I was asked to give here a very short summary at the end. Okay, if you want, this is it. A world model now in this new view is nothing else than a probabilistic approximation of the environment's dynamics seen through the lens of the internal representation of an agent. This has a beautiful idea. I wouldn't call it a consequence. It's just a thought. No? If we have these huge foundation models, no? This, I don't know, O3 or go with R1, the new one, no? And they tell us here, this work supports now the hypothesis that implicit world models emerge during the pre-training, during all the training phases here of the AI, therefore enabling here the generalization of the AI system to unseen objective. That means we have, if you want, this kind of emergence of intelligence, quotation mark, especially in the reasoning and the planning phase that we have that are so important that define here the action of our agent. Now I would say from a physical point of view, this would make sense. Because if you have a dislocated patch of little islands of reasoning and little action sequence planning segments somewhere floating in space, but you do not have a coherent, closed reasoning system, a world model, then you cannot generalize to unseen functions. But if you have an implicit world model, and it might be an even tiny, little, stupid, incorrect, but you have a view of the world as an AI, then this would enable you to have here kind of emergence of some new level of intelligence to unseen objectives, because you understand the logical interconnect between all the different elements of your world model. And if now a new interaction pattern is detected, you would be theoretically logical able to deduct here the causal inference patterns. So, if you see the learning process of an AI or an agent from this particular perspective, that it has to develop its own world model, an implicit world model, this would explain for me, a simple-minded person, why you could say, okay, if I have then unseen objects, this is not the emergence of intelligence and suddenly the hyper-intelligence emerges. No, it just has a coherent world model, and it makes sense that now, given all the other objects are placed, now if we add a new connection, a new edge into this, let's say a graph structure, it makes sense that it integrates in a coherent way, and therefore we have some, quotation mark, new intelligence. But of course, and you know this, the complexity level of these world models are defined by the capabilities of the LLM. So just because you have a world model as an 8B, 8 billion free trainable parameter model, does not mean you have the correct world model. It just means that you have some crazy, polarized, non-coherent, whatever, world model, kind of, and it needs the complexity of the internal structure here of the AI architecture that we can really then say, okay, these world models become more and more coherent in their planning, in the reasoning process, so we can increase the complexity now of our task, given we have a higher complexity of the world models. But this also means, and now coming back to me here in my, what I called it, I don't know, hyper-manly intellectual pose here, that's when I operate now with O3 from OpenAI, I have no idea at all about the internal world model of O3. I don't know, since it's a proprietary model, how O3 was pre-trained on what complexities in the real world. I just interact blindly with it, and I'm just hoping for a correct solution for a machine that has never seen the real world. I think this is currently, for me personally, the state of AI. This is our theoretical understanding of, if you call it intelligence of an artificial intelligence system. It is here the coherence building of an internal world representation. I like this idea. So therefore, here you have me stepping into a brand new world where the world outside is an internal representation by an AI, optimized given its pre-training data and its training procedures, but it might be absolutely different to my world, to my understanding, to my experience, to my beliefs, to my values, because the coherence in my world model might be completely different to the AI coherence. And you might say, but wait a minute. This was just about logic. This was just about causal reasoning. This was just about planning. This was just about mathematics. This was just about logic. This was just about physics. But we have something that is so much better, yeah? We have vibe coding. And yes, of course, you're right. We have vibe coding. Yes, and I have here a video on vibe coding done professional to create your own apps in 15 minutes. Yes, of course. But let me ask you something. Do you really think, honestly, if we do here an SVE agent benchmark analysis, so we check how good is AI in developing high-performance software, what do you think the benchmark results will be? Well, let me ask it in a different way. What could possibly go wrong if I look now at the latest software agent benchmark analysis? If you want to find out, hey, why not subscribe? And I see you in one of my next videos.